All right. Welcome to Math 1 class today. First of all, a quick note to the online audience. Unfortunately, it seems the sound is not working as it should today. So I've tried turning on the notebook microphone to get some sound here, but it's probably not the quality that you're used to. I hope it still works, at least reasonably well. All right, so welcome everyone. This week will be the last week of new topics in this class. Specifically, we'll discuss integration today, tomorrow, and on Thursday. Again, I think that at least some of what we will discuss is already known from school, so hopefully it won't be too hard. I'll try to go over the details briefly, and then as usual, we'll have a look at some examples. So, first, a couple of basics. When you do integration, the idea, the goal is basically to determine the area between a function's graph and the x-axis. So you have a graph, like this blue one for example, and you want to determine the area here, and here, and here. Preferably we also like to know which of those is below and which is above the axis. To make this a little easier, we'll start with something that seems more reasonable. We restrict ourselves to a very simple class of functions for which this task becomes easy, and that is the task of step functions. Step function basically is a function that is constant on a certain interval, and then possibly jumps somewhere else, like this blue function. That's a step function. Right? And at the boundaries of these intervals, the function value doesn't really matter. So whether the value is the same as in this interval, or as in this interval, or somewhere else completely, that's just single points. And if you compute the area of those single points, of course, you don't have any influx. Right? The width of that single point is 0, so it doesn't matter much where it jumps to that. The only thing that does matter is the intervals of positive, like this one. And of course, it's easy to determine the area for step functions. All you have to know is the intervals, and just basically each of these intervals defines a rectangle. And determining the area of a rectangle is easy, so just sum up over all these rectangles and be good. All right. Formally, this definition is for defining what a step function is, mathematically speaking. What you need is first some interval, basically a large interval where all of this lies in. And then you have what we call a subdivision on that interval. Well, this is the interval. Well, subdivision is just a number of points in that interval. The first point is always the left boundary of the interval. The last point is the right boundary. And then there's a number of points somewhere in the interval, right? That subdivision points are numbered in a way such that the values are increasing. So x1 comes after x0, x2 comes after x1, and so on. And then you can define what a step function is by simply saying, well, a function on that interval is called a step function if there is a subdivision of the interval, however many points I need, finitely many points, such that the function is constant on all the consecutive intervals defined by the subdivision. Right? So I have this interval, and the function is constant on that interval. This interval, and the function is constant on that interval, and this interval, and the function is constant on that interval. Again, what it does on the subdivision points itself, here for example, does not matter. And of course, it doesn't say anywhere that the subdivision has to exactly correspond to the steps. So, for example, if I add one more subdivision point in here, that's totally fine, right? So basically, I divide this interval here into two parts. and the function can take the same value in both of these parts. Yeah, that's great. You would, for example, do that if the function jumps anywhere else, and then it comes back to the original value. Okay, and for these step functions, we can then define how to compute the area between the x-axis and that function. And we call that area an integral, or rather what we call the integral is the area together with the sine. Right? So we have the step division, we have the step function, and the subdivision corresponding to that step function, we have the intervals, and the function is constant in each of these intervals. Gamma k is the constant function value for the kth interval. And then what we do is we define the so-called integral. This is denoted in this way. So integral over the function s of x dx. This dx is a formalism that tells you what the integration variable is. So in this case, the function depends on x only, so it's pretty obvious what the variable should be. But in some cases, you have functions that depend on more than one variable, and that is useful to know which variable is the one that we integrate over. Right, and here's the interval, or you can also write the lower upper boundary of the interval below the buffer of the interval sign. Right, and that is then simply defined as the value of those rectangles. Right, so this is one side of a rectangle, this is the other side of a rectangle. And of course this can be positive or negative. So a value, function value above the x-axis will be counted with a plus, positive. If the value is below the x-axis, we count the value negative. Right? So this is basically the area with the sign. And we just sum up over all the intervals of our subdivision, and that's what we call the integral. Right? So that's kind of the sum of areas with real signs. All right, very simple example. Here's a step function defined on the integral from 0 to 6. 3 different steps. It's 3 from 0 to 2. It's minus 2 from 2 to 5, and then it's 1 from 5 to 6. So it looks like this, 3 minus 2, 1. A possible subdivision is to take exactly those points. So we start at 0, we end here at 6, and then we need 1 point here at 2, 1 point here at 5. We could take more, those are the ones that we need. And then this results basically in these 3 rectangles here. This and this one is a positive value, and this one is a negative value. So if we now, for example, sum up from 0 to 2, right? From 0 to 2, it's just about this interval here. That means we're computing this area, and that's 2 times 3, so 6. The area of this one is the integral from 2 to 5. 2 times 3, so that's minus 6. This here is the integral from 5 to 6, and the area is 1 times 1, so that's 1. If we integrate that function over the whole interval from 0 to 6, we just sum up those values. So we get 6 minus 6 plus 1, so the total integral is 1. If I'm asking for the total area, of course, then you would count this area here with the positive sign instead of the negative sign. For the integral, it's negative. If I'm asking for the area, you have to be aware of that. So formally, for the area, we would integrate not over s, but instead over the absolute value of s. Right? So in other words, you need to figure out where the function is positive or is negative and invert those to places where it's negative. Right? One other example, integral from 1 to 4, for example. Basically means we're starting here, so this is 2, 3, 4, so we'll stop here. And that means we have this rectangle here, and then we have this part here. So So we get 3 for the first rectangle and 2 times minus 2 for the second one. That's minus 1. Right? Here's the area. Basically, the only difference to this one here is instead of minus 6, I flip that to plus 6. Okay, so that's integration to step functions. Hopefully nothing surprising here. Here's a few properties of the integral that we define this way. Should be pretty obvious. Well, the first one is maybe not that obvious. The integral is independent of the choice of subdivision. You actually have to prove that to be precise. I'm not going into the details here. I think from the visualization, hopefully you believe me that this actually works. Of course, a constant function on the whole integral is also a step function. And this is an important property for applications later on. If we have 2 step functions and constants lambda, then we can take a look at basically this composition of the 2 step functions. So we take lambda 1, s1 plus lambda 2, s2, defines a new step function. And this is, again, a step function. You can just basically mix the 2 corresponding subdivisions and get a new subdivision that works for that new function as well. This is, of course, nothing else than a linear combination of those 2 functions. So in other words, a linear combination of any 2 step functions, you get a step function. So you could say, formally, this space of all step functions over an integral is a vector space. Once you have that, you can also state that the integral operates on that space, so basically that it takes a step function and assigns a real number as a value to it. So we have a mapping from that space of step functions to the real numbers. And if you interpret the integral as a mapping like this, then it turns out this is a linear mapping. So maybe to put it in simpler terms, this relationship holds. So if you have an integral over a linear combination, you can just split that up into 2 integrals, and you can take out the constants. And this is what we frequently do. Just as a remark, a mapping like this from a vector space that is composed of functions to the real numbers, mapping like this is often called functional. So you'll sometimes read that the integral is linear functional. But you don't have to, I don't have to know that just in case someone on the anyway. And finally, the integral also has kind of a monotonicity property. If you have 2 step functions where one is always less than equal to the other for all x's in the interval, then this also holds for the integral. From the definition, it should be obvious again. So once the function is lower than the other, of course, the value, the area that is enclosed by the lower step function will be less than by the higher one. Yeah? You only have to pay attention that this holds for all x in the interval. So if it is above one first and then moves down, then of course that can balance each other out. Alright. Integration of step function. That hopefully is the easy part here. Any questions on that one? Yes.
How small can the intervals be which you define the different steps? So I was just wondering if it's not possible to approximate this integration in general by just making these intervals very small.
Exactly. That's the idea that we're going to use right now. So the point is these intervals, those can become very small, infinitely small actually. Right? The only important point for a subdivision, you need finitely many points in a subdivision, but of course, what you can then do is make things very small and then use a limit process and see if the limit or making these intervals smaller and smaller, and you get more and more points if that limit actually exists. And that's what we use for defining the integral next. So here's the idea of what is called the Riemann integral. Again, we have an arbitrary function now, not a step function, and we want to define an integral for that. What we do is we approximate that function by step functions. And one idea to do that is, you can say, well, again, let's take a subdivision. Any subdivision will do. And then we'll define a step function that is related to our blue function by simply saying, let's take the lowest value that the function has on the interval and define a step function that just assumes that lowest value. This green one. Here, 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 and here. And that should be an approximation to the area below that blue curve. It's not exact. I mean, this, for example, this value is missing, this value is missing, and this is missing, and so on. But if you take more and more points for your subdivision, hopefully this approximation will get better and better. And the idea is exactly that. We take more and more points until the subdivision is so good that hopefully we'll get a decent value for the area below that curve that we actually want. Now, of course, we're using this green curve here. That's somewhat arbitrary. And we just took the lower function value on that interval. We could also use the higher function value, like here, for example. That would be this pink curve. We get this, and this, and this, and this. And of course, those function values don't have to be on the boundaries as they were with the green curve. For example, with that pink curve, we get the maximum here. So that would take this value and not that or that. And again, we could use the very same idea. This time we get an upper bound. So the area that we get by using this pink step function here, that's too large. But again, if we make the interval smaller and smaller, hopefully the approximation will get better and better, and we will get closer and closer to that blue curve and approximate the area we're actually interested in. Question, of course, is does this actually converge? And when does it converge? And do both of these approaches lead to the same result? Hopefully they do. So if the function is somewhat reasonable, we would expect that to yield the same result. So what we do now is we say, well, we just define the integral in that way, and any function that yields a reasonable limit, and the same limit for the lower and the upper bound, we call that integral. So we just say those are the functions that we can integrate. For all the other functions, well, you might have to think again. And it turns out this covers a very large class of functions. That's sufficient for most applications already. All right, more formally, we first need to define what an infimum and a supremum is. Basically, think of that as something like infimum, something like a minimum, and supremum, something like a maximum, but it doesn't have to be assumed. Right? So the maximum is always something that is actually assumed by the function. The minimum is always assumed by the function. The supremum and the infimum are similar things, but they don't have to be assumed. In other words, more precisely, the infimum of any set of numbers, usually will be function values in that set, infimum of any set of numbers, is a lower bound. So this B is the infimum, that's a lower bound, so it's less or equal to all the elements of that set. And it's the best lower bound we can get. So what the best means is we can't improve it. We can't find lower bound that's higher. Right? More formally, if we have any other lower bound that is not higher than E. That's what infimum means, the best possible, the highest possible lower bound. And supremum is the analog for the upper bound, so supremum of a set is the best possible upper bound, meaning it can be lowered. So again, this upper bound is greater or equal to all elements of the set, and if we find another upper bound, then it can't be smaller. There's no better upper bound. Okay? So the infimum is the largest lower bound, the supremum is the smallest upper bound. And in contrast to minimum and maximum, they don't have to be assumed. As a quick example here, consider this interval from 3 to 5. 3 included, 5 excluded. Then the infimum of that interval is the best possible lower bound, and that is 3. In this case, it's also the minimum, right? So this interval has a minimum. The supremum, the best possible upper bound, is 5. But 5 would not be a maximum because it's not included in the set. Right? A maximum would have to be in the set. So 5 is a supremum, not a maximum. Similarly here, if we add the number 7 to that set, then of course the lower bound and also the minimum are unchanged. The supremum is now 7. We can't lower that, because if we did, we would lose that number here. Don't want that. Right? So that is now the best possible upper bound. And in that case, 7 is included in a set, so 7 is also a maximum. Right? Final example, consider this set be 1 over n for n in the natural numbers, 1, 2, 3, 4, 5, and so on. The infimum of that set is 0. We know that it converges to 0, so it gets as low as you want, as close to 0 as you want. So 0 is the best possible lower bound. If we increase that, we'll find some n where 1 over n falls below our increased bound, so that doesn't work. 0 is not included in the set, so it's not a minimum, so it doesn't have a minimum. But of course it does have a maximum, again, the highest possible value for setting n to 1, so 1 over 1. That means the supremum and the maximum is 1. All right. So now that we have those notions, basically when we use the notion of minimum and maximum, if those are not included in the set, that's why we do infimum and supremum. And we need that to define the Riemann integral. We do that by defining those two approximations. We call those the lower Riemann sum and the upper Riemann sum. So we have an interval, we have a function defined on that interval, and say that function is bounded on the interval. For example, that would be the case if it's continuous. And then what we do is we take a step function where the values are lower than that of f of x for all x in the interval. For example, the one that we saw in that sketch, right? So the green function has values lower than the function all over the interval here. So that's a lower approximation. Then we compute the integral of that step function. And we say, well, we want to refine that to find the best possible value, the maximum of that, if it has one. Or if it doesn't have one, we settle for the supremum. Right? Maybe that maximum is never achieved, but now we just take the supremum. And of course, we can do the same thing from above, so we take our step functions that are higher than the actual function value. We take their integrals, and we want that to be as low as possible, to be as close to the function as possible. So in this case, we take the infimum. And then we say, well, if those two happen to coincide, then we call that value the integral of the function f. So the function f is called Riemann integrable over the interval if those two Riemann sums, so the upper Riemann sum over I are equal. And we call the value the integral of f over I, and we write it in the same way like that. Yeah? Or again, upper and lower bound. Okay, just for terminology, that function here is usually referred to as the integrand, and the interval is sometimes called the range or the domain of integration, whatever you prefer. Okay, two more notations that or settings, conventions that we use, and that of course are corresponding to the definition of the integral step functions. So you integrate a step function over an interval of 0 length, and of course the value will be 0, and we just define the same thing for arbitrary functions. And if you reverse the order, so if you have an interval from A to B, and you integrate from B to A instead, right? So from the right to the left, basically you reverse the direction of one side of the rectangle, and we say what that does is basically reverses the sign of the area that we get. So that's the same thing as integrating from A to B, and then negating the result. Right. Here's a quick example to show you that not every function is Riemann integrable. But you have to, usually you have to define pretty weird things for that to happen. So most functions that we are encountering in practice will be Riemann integrable. This is really pretty weird beast here. So on the interval from 0 to 1, you just say, well, this interval is composed of rational numbers and of irrational numbers, right? Rationals are the one that can be expressed by a fraction of integers, a over b, and irrationals are the others. And you say, well, I set the function value to 0 if the input is rational, and I set it to 1 if the input is irrational. And of course, rational numbers and irrational numbers are dense, as we say, so they're as close as they can be. More precisely, if you take a neighborhood around a rational number, there are always irrational numbers contained in the neighborhood and vice versa. So whatever interval you define, no matter how small, in this 0, 1 here, will always contain both rational and irrational numbers. Right? And that means the lower real sum is always 0, because it has to be below that function value, and the upper real sum is always 1, because it has to be above that function value. Right? And that means, of course, those two will never coincide. You can make your intervals as small as you want, it will never work. And that's an example for a function that doesn't have the Riemann integral. Of course, there are ways of getting around that. There's still functions that we're just not able to handle. But for a large class of functions, there is another possible definition of an integral. We're not going to cover this. Just in case you stumble upon that somewhere, that would be the Lebesgue integral. Like this, Lebesgue integral. For all the purposes of this course, and also for the course Mark 2, the Riemann integral will be sufficient. All right. So, interesting theoretical question to close the theory part more or less. What functions are integrable? Is this a sufficiently large class? And it turns out it's easy to find a very large class of functions that is integrable. If we have a bounded interval and a function that is bounded, and one more property, either it's monotone or it's continuous. And you can even make exclude a number of points from that continuity or monotonicity property. So you can exclude finitely many points. It means finitely many jumps are allowed, that's fine, as long as all the rest is good. Then f is integrable over the interval. So what it means is any function that is at least piecewise continuous over a bounded interval is always integrable. And that should cover pretty much, well, most of what we have seen so far. Okay, so the applications that you will encounter non-Riemann integral functions should be a very, very extension. Good. Any questions about that theoretical part? Good. little more theory, fortunately, we'll get to practicing that. First, a couple of useful properties of the integral. We covered some of those for step functions already. And this is just to really summarize that all of this can of course be carried over to this more general definition of Riemann integrals. So if we have two functions that can be integrated, then again we can look at a linear sum like this here. And then its linear combination is again integrable, and again this linearity property here holds. So we can decompose that into two integrals, and we can take out the constants. This is referred to as the linearity of the integral, as with step functions before. The monotonicity property also holds. If one function is less or equal to the other, then the same thing holds for the integral. In particular, that means the integral function is always less or equal to the integral of the actual value of the function. This property here, something that is, we didn't list that for step functions, but it's also pretty obvious. If you take an arbitrary point in the interval, you can just split the integral at that point if you want to. So if you integrate over the interval, it should be the same thing as integrating up to that point, and then adding the integral starting from that point to the right boundary. That's called additivity of the integral. And of course, it also works for step functions. You just refine your subdivision. And almost finally, you have some pretty obvious bounds here. So if you consider this integral of a function, like this one, you have a lower bound, this green, so the lowest function value f takes. And you have an upper bound, this pink one is the highest function value f takes. Then of course this green area here will always be less or equal to the actual integral, which is the blue area, and this integral is less or equal to the pink area. But that's all that says. If you have a function that can be integrated, then you can take a look at two functions that arise from that. This next part here says, well, those can also be integrated. Those are usually referred to as f plus and f minus. What we mean by that is, well, f plus is the positive or non-negative part. So this blue thing here is a function. Then everything above the line is f plus. So this is not above the line, that means f plus takes a value of 0 here. Then the function rises above the axis, so this is f plus, and then it goes below, so f plus stays at 0. Basically, you cap the function from below at the axis. F minus is almost the same thing for the negative values. So basically, you take this, then you cap here, you take this. Only difference is you flip it. You want f minus to also be non-negative, so instead of taking the actual negative values, you negate that and take the corresponding positive value. So this pink function that will be f minus in that case. The idea basically is that you can express the function f in this terms here, so it's f plus positive part minus negative part. And that is useful if you want to talk about the area enclosed by the function, because this way you can do away with signs, right? So in particular, the absolute value of f can then be expressed as f plus plus f minus. And that means if I'm interested in the area, so this area plus this area, no signs plus this area, then I would have to integrate over the absolute value of f, or I could just integrate over that f plus plus minus. So in other words, you do what you intuitively would do. You just split f at those points here, where it crosses the lines, and then you integrate that part, add a negative sign to flip it over here. You integrate that part with a positive sign, and you integrate that part, and again, you flip it. Yeah, so it's just a complicated way of expressing what you would hopefully do correctly. All right, one last, almost last theoretical result. We won't need that very often, but it's a useful tool for proving some of the more advanced results that we will need very often. That's basically why I listed it here. That's the mean value theorem of integration. And what that says is, well, if you have a function and you integrate that function over an interval, then you can express that value of the integral through the area of some rectangle, where one side is exactly the interval length, and the other side is some function value. You just don't know the function value, so you just don't know the corresponding extilde. Right? So what the theorem says is there exists some extilde in an interval such that this holds, but not telling you where that extilde is. That would be too easy. Right, as a theoretical result, it's necessary to prove some of the things that we are going to prove, but you'll rarely ever find that out. Good. Questions so far? A lot of theory to be carried out when we get to the applications, but I promise we're not that far from it. Final building block. So, of course, in practice, you are probably not that interested in computing these Riemann sums, doing this limit process by hand. You can try that if you want to. For simple functions, I think you can handle that, but it turns out to be pretty obnoxious, so nothing that you want to do on a regular basis. And that is why we need some more advanced tools to actually be able to compute integrals. Here's the tool that we will use. And that's coming from this area computation, somewhat surprising connection to derivatives. Here's the main theorem of calculus. If we have a function on an interval that is continuous, then we can define a new function, call that capital F. We just fix some point in the interval, call that A. Yeah. Can be the left boundary, but it doesn't have to be. Choose whatever you want. And we define an integral that depends on a parameter, call it x. So we integrate that function f from a to x for any x in the interval. Could be to the right or to the left of it, doesn't matter. And we call it value f of x. And then what this theorem says, well, this f of x is actually a pretty nice function, because that is a function that is differentiable. So it's not just continuous, it's even differentiable, and its derivative is exactly the function that you start with. So in other words, integration is kind of the inverse operation of differentiation, as it turns out. And this is really useful because we know how to differentiate a function, right? So if you have a function, in many cases it's easy to guess which function do I have to differentiate to get that. Right? So it's easy to guess how this function f should look like. And that's the thing that we're going to use most of the time to compute integrals. I'll skip over the proof. This is one place where we need that mean value theorem of integration that we just discussed before. Just pointing that briefly. A naming convention. If we have a function on an interval and a function capital F that is differentiable and has this property f prime is equal to f, then this capital F is referred to as an antiderivative of the original function. Yeah, so we either use the terms integral or antiderivative, depending on where the argument comes from. And now here's a way to compute integrals, or basically the first step in that way. If we have two antiderivatives for the same function, how do they differ? One question that has been asked yet is, if I have an antiderivative and maybe another, which one do I take to compute the integral? Which is the right one? And the answer is, it doesn't matter. This is what Tramark says. Because what it says is, well, if I take the difference of those two functions, differentiate that, it's easy to see that this is f minus f, so this is 0. Right? And if the derivative of something is 0, then that something is a constant. So that means two antiderivatives for the same function differ only by a constant. And now we're ready to compute integrals, finally. So if I have a function I want to integrate, and I have an antiderivative for that function, 2 points to compute the integral. Then I can just compute that by evaluating the antiderivative at the upper bound, at the lower bound, and then take the difference. At the upper bound minus the lower bound. Right? And of course, if two antiderivatives only differ by a constant, well, if I take the difference here, this constant doesn't play a role anymore. So that's why this was important. Okay, so now I have a way of computing integrals in a, maybe not easy, but reasonably easy way. I have to guess an antiderivative of a function, and then I can just use that formula. Again, let's skip over the proof here. Just quick notation. Again, if I have a function f, then I do have not just one, but a whole set of antiderivatives. Basically, you take any antiderivative, add a constant, you get another one. This set here is sometimes referred to as the indefinite integral of f. And it's usually denoted in that way here, integral just without boundaries. Yeah, that just means a set of all possible antiderivatives. Usually, we write something like this. This is some f antiderivative plus c, and by this plus c, what we mean is, well, add any constant you want or need. It doesn't matter. So this is common notation to denote that whole set, and basically saying choose your constant as you like. Okay, and two other notations that we'll frequently use. I guess one of those will be familiar, maybe not the other. For evaluating an integral, evaluating an antiderivative, we usually denote the antiderivative in brackets, and then we just add the boundaries on the right hand, and that means this evaluation. Another common notation for the same thing is this one. Use whichever you prefer. I usually use that one. Doesn't really matter. Okay. Any more questions at this point? Otherwise, we're finally ready to see some examples. Good. So let's start with these examples. Here's an integral of a polynomial x squared plus 2x minus 3. In this case, we integrate from minus 1 to 1. Doesn't matter much, just makes it a little easier. Functions of this kind, what you usually do is you start by using the linearity property of the integral. So you split it up in this case, 3 integrals, one for each of those sums here. So we have an integral over x squared, an integral over x times 2, and an integral over 1 times minus 3. Of course, I'm only doing it in this way to show you how you would do that. You're free to not write that down in the future. Just do those computations in your head and you get it. And now what we do is, for each of those functions, we guess the antiderivative, or one possible antiderivative. Doesn't matter which one we choose. So the question is, which function, if I differentiate it, yields x squared? And of course, you know that there has to be some x to the third function, right? So something like this. Now, if I differentiate that, I get 3 times x squared. I just want 1 times x squared, so I divide that whole expression by 3. Right? And now differentiating this yields 3x squared over 3, so that's exactly what we wanted here. Okay, so this here is an antiderivative for x squared. Same thing for x. You know, to get x, you need to differentiate something like x squared. Again, if I differentiate x squared, I get 2x, so I need to divide that thing by 2 to just get x. So the derivative of that is 2x over 2, and that's what we wanted here. And for 1, that's easy, you just differentiate x, you get 1. Okay? Now we have our antiderivatives, and then we can evaluate the integral by substituting the upper and the lower bounds into those antiderivatives. What we do is evaluate that at the upper bound minus evaluate that at the lower bound. So 1 to the 3 over 1 minus 1 to the 3 over 1. Same thing here and here. And then we just do the computations, and this is the value you should get, minus 16 over 3. Alright? A little more complicated, not that much actually. This integral here, e to the minus 2x. Again, we need to come up with an antiderivative. We can do that by just guessing. We know that the derivative of the e function to the x is the function itself. So maybe let's take a wild guess and try to differentiate that function directly, see what happens. If I do that, the function reproduces, and then I have to use chain rule multiplied by the derivative of the argument, and that is minus 2. Right? So that means I'm almost there. I want that function, so I need to get rid of this minus 2, and I can do that by simply dividing over minus 2. Right? If you check that again, differentiate that term, you get exactly this, and that is what you need. So this here is the indefinite integral. As I said before, you can add any constant, you get another antiderivative. One other pretty common class of examples that we'll deal with a lot this week are trigonometric functions, sine and cosine. Again, we know the derivatives of sine and cosine, so it's easy to guess antiderivatives in many cases. For example, if you have a function like sine of pi x, well, you know that the derivative of the cosine is the negative sign. Right? So my first try would be differentiate the cosine of pi x. That will yield minus the sine of pi x times pi. And then I have to get rid of the minus and of that pi. So let's divide by minus pi and we're good, right? So this here is an antiderivative for this. And that means I found my integral. So this is how you would work with trigonometric functions. We've talked about polynomials before. Of course, we can also use fractions of polynomials, see what we can do there. If they're easy enough, so in this case we have 1 over x to the power of 3, or x to the minus 3. And if you do that, pretty much the same differences you would hold there. So as an antiderivative, I try something like x to the power of minus 2. If I compute the derivative, I get minus 2 x to the power of minus 3, so I just need to get rid of the minus 2 and divide by that. Of course, that approach only works if what I need to get rid of is actually constant, right? If it contains an x there, that doesn't work anymore. Because you then have to use quotient rule for the differentiation, and it will get rid. You don't want that. You can avoid it. Alright, but in this case it works out nicely, so it's pretty much the same rule as with polynomials. You get minus 1 over 2 x to the power of minus 2. One exception to be aware of, x to the power of minus 1. You can't just say, well, the integral is x to the power of 0, because that's 1, and the derivative of 1 is 0, so that doesn't work. But we do know a function that has this derivative, and that's the ln. Right? So the integral of 1 over x is the ln function. And almost the last example is also looking at square roots. I have a square root function. We know how to differentiate the square root function. You do remember we could write square root as x to the power of 1/2. And then what happens if we differentiate that? We get 1 over the square root, or if you want to end up at that, a good first guess would be to try and increase that exponent here by 1, so x to the power of 3 over 2. If you differentiate that, you get 3 over 2 times x to the power of 1/2. Right, so you're almost there. You just need to get rid of that constant, and you do that by dividing by that constant, or multiplying by the inverse. So this here is the antiderivative that we're looking for. And if you want to write that in different ways, you could rewrite it like that, or like that. Okay, so square roots also work. One last remark. I said this many times, but I'll say it again. If you want to determine area, please pay attention that you don't integrate over f if that function takes negative and positive values. Instead, you need to integrate over the absolute value of f, or f plus minus, if you remember that. So what you need to do usually is to find the points where the function crosses your axis, or the roots. For example, if you consider this function here, looks like this blue function here. If you want the area enclosed here, plus that, you first have to find those roots here. And then you take this new function. What it means in practice, of course, is to split up the integral. So instead of integrating from -3 to 3 in this example, you go from -3 to -2. That's the first splitting point. Then from -2 to 2, you integrate minus f instead of f. You flip it at the axis. And then from 2 to 3, you integrate f again. And in this case, you make sure to count all the areas with the same positive sign. And the rest is just integration as we used to. In this case, you get the value 23 over 6. All right. I'm talking a lot now. Sorry about that. Lots of theory. But I think the applications up to this point should be fairly straightforward. So let's take a look at the first example. One example that you hopefully already had a look at is this homework problem here. We have two functions, homework 14.1, two functions, both polynomials. And your task is to determine the intersection points of those graphs and then the area enclosed between the two graphs. So a little more complex than we have done already. Basically what we want to do now is, give me a second, quick sketch. So we have one function that might look like this. Say this is f, we have another function. Actually, this is more like g. Let's call that g, not confuse you too much. No, sorry. Let's call this f to not confuse you too much. And then I have one other function, g, that might look something like this. And what I'm looking for now is the area enclosed between those two functions. So those are the intersection points, and I want the area between those two curves. Right? And hopefully that was not too hard of an exercise. So let's have a quick look at your results. Just give me a second to pull up the quiz. Here we go. So here's this week's tweetback link. And let's see what area value you got. Hopefully it was one of those that I proposed. Give you one more minute to figure that out in case you haven't done so yet. Let's switch back here. All right, let's have a quick look at the results here. So most of you say the value is 104 over 50, and you're of course right again, so this is the value that you should obtain. As most of you got this correct, this begs the question, do we have to discuss that? So I opened a quick tweetback vote. Maybe just say yes or no briefly. I'll give you 30 seconds, and then we'll see whether we need to talk about that. Right, most of you seem to be in favor of doing that. So here's your results. So let's have a quick look at that problem. Let me pull it up again. Here you are. All right, page 41. Inspired by this problem, by the way. I don't think the numbers are the right ones, but a problem like this has been on some older stuff. I don't remember the year. Alright, so we have f and g, those two functions. First thing we need to do is we need to find those intersection points. So this and this, the x values thing. So how do we do that? In other words, what we need for the intersection point is we need to find the roots of the difference. So for the intersection points, what we want is points where f of x is equal to g of x. And that's, of course, the same thing as asking f of x minus g of x. Where is that 0? Now, if we take a look at those functions, f and g, or f of x minus g of x, that would be, let's see, x to the 4 minus 5x squared plus 4 minus 9x squared, so plus 9x squared minus 9. So we get x to the power of 4 plus 4x squared minus 5. Okay, now that is almost a quadratic equation. But instead of x squared, we have x to the power of 4. But the good news, we can just use a substitution and say, well, let's define y as x squared, and then this can be written as y squared plus 4y minus 5. And this is a quadratic equation, right? So finding the roots of that is easy. We have a formula for that. y12 is equal to, let's see, minus 4 plus minus the square root of 4 squared, that's 16. Minus 4 times 1 times minus 5, so that's plus 4 times 5, that's the same. And we divide that by 2. Okay, so this is minus 4 plus minus the square root of 36 over 2. The square root of 36 is 6. So what we get is, let's see, minus 4 plus 6 is 2. 2 over 2 is 1. And the minus 4 minus 6 is minus 10. And minus 10 over 2 is minus 5. Right? Now remember, x squared was y, use that substitution. So of those two solutions here, that one is not possible. Right? X squared is always non-negative, so it can't be minus 5. And that means the only possible solution is 1. And that means x could be minus 1 or plus 1. And there we get our intersection points. And minus 1 and plus 1. And we're asking for the points here, so the point, of course, is minus 1 as the x coordinate, and to get the y coordinate, we just substitute it to one of those functions, doesn't matter which one, you have the same value. So maybe let's use g. G of minus 1 is minus 9 plus 9, that's 0. And for 1, of course, the value is the same. So it's 1, 0. Alright, so those are the two intersection points. And that means to compute the area between those two curves, we'll have to use the integral that goes from minus 1 to plus 1 on the x-axis. Now, what we still need to know is, what about the function values? Are those positive? Are those negative? What can we say about that? Well, in this case, it's easy to maybe just compute one value, right? So, for example, maybe 0 is easiest. And so if we take 0, for example, f of 0 turns out to be 4, g of 0 turns out to be 9. So in this case, at 0, g is above f. They only intersect at -1 and 1, so that must be true for the whole interval. Right, so we know here is g is above f. So this could be g. This could be f, something like that. So for that whole interval, f is going to be below g. F below g. Alright? Here's -1, here's +1. And that means if you want to get the area, we'll start with the function g, because the area below g, this one here, that's going to be larger. And then we subtract the area below f. Right, so what we want is the difference. Yes, there is a difference. So that means this red area that we want that can be expressed by the integral of g of x dx from -1 to 1 minus the integral of f of x dx from -1 to 1. Okay, so this is what we need to compute. And it's probably easier to first put those together as one integral. So we compute the integral over g of x minus f of x dx. The integral is linear, so we can just do that. We have computed that function already, I think. No, we computed the inverse. So, if we do that again, what we get is the inverse of what we have 4 minus x to the 4th minus 4x squared plus 5 dx. Remember we did that computation already. And then all we need to do is integrate that. I won't split it up into 7 intervals, but of course that's exactly the steps I'm doing in my head. So I start with x to the power of 4. I just take this minus sign around. Integrating x to the power of 4, well, we need something like x to the power of 5. If you differentiate that, we get 5x to the 4. So we need to get rid of the 5, and that means it's x to the 5 over 5. And then we have minus 4 times x squared. Integrating x squared is x to the 3rd. Differentiating x to the 3rd will get us 3 times x squared, so we need to get rid of the 3. So let's just divide by 3. And finally, 5 times 1, integrating 1 simply means x. And we integrate that from -1 to 1. So all that's left is evaluating that. And if we do that, we get upper bound first. So -1 over 5 minus 4 over 3 plus 5. And then minus the lower bound. Lower bound is -1. -1 to the power of 5 is again -1, so -1 is +1, so we get 1 over 5. Then we get x to the power 3, so minus 1 to the power 3 is minus 1, minus 4 times minus 1 is plus 1, so we get plus 4 over 3, and finally minus 5. And then we just need to simplify that. If you do that, it turns out this is 104 over 15. All right, any questions about that example? Let's have a quick look at the tweetback question, see if there's anything I need to discuss. Maybe one quick remark. So I can see some questions about linear subspaces and matrix games and so on. It would be really helpful if you could collect those in a separate tweetback. So I can discuss all of those next week when we have time for all those questions. Because that week I'd like to concentrate on integrals to get that done properly, and then next week there's Q&A, and I'm open to questions of all kinds. So I'll open the tweetback link. I'll put that link on the Moodle page for next week, just after this course here. And it would be great if you could just collect all your questions for next week in that tweetback feed. Right? So we can take a look at that and take out all the questions that are still of interest. Let's see. That's about audio quality. I know for the live stream audio quality is really bad. Sorry about that. I couldn't find a fix for that, unfortunately. Substitution and partial integration. I guess, yeah, we talk about those next, but I guess it doesn't make sense to open that discussion today, so I'd rather defer that to tomorrow. We will talk about that, and we'll see lots of examples about that. Do we need to know higher order square roots, like square root of 324? Well, I guess maybe not. I'd say up to 10 squared, 11 squared, maybe 12 squared, that would be nice, but probably higher, no. I don't have the wrong input source selected, I checked that. Yes, so one question is, at 41, so here what I did is, as you remember, I checked which of those two functions is above the other, so that I got this order correct. So instead of taking f minus g, I opted for g minus f. Right? I could, of course, also reverse that, and then just take the absolute value of the result. I know those don't intersect in that interval. So one function is on one side and the other is on the other side, and they don't intersect within that interval anymore. I have my intersection points, and those are the boundaries. So using f minus g, and then just negating the answer if necessary also. Just make sure to not state something like the area is minus 70. That will get you at least 1 point deducted. Okay, I just answered that. And I just answered that. Could you explain all kinds of brackets quick? So I guess you're referring to my interval notation, which I think I clarified on one of the first videos, so you can watch those again if you want to. Just for a very quick recap, if I have an interval like that, basically there's two options for the boundaries. I can either exclude them, that means I'm excluding my boundary, I'm using this notation here, or I can include them, and if I want to include them, I'd use this notation here. Right, so this means include B. And of course, I can also reverse that, so this would be A included, B excluded. As an alternative, it's also fine to use this notation for exclusion. Right? So if you're more familiar with that, feel free to use that. Same thing. hope that was actually what this question was about. Why didn't you substitute -1 in the end? I did. So just to clarify, here's where I substitute the upper bound. That was 1. And here is where I substitute the lower bound. That is -1. I subtract that. Right, so please mind this minus sign. And also please make sure to apply that minus sign to all of those terms, right? All of those get a minus sign, not just the first one. Common mistake. So please don't forget those brackets. I don't get that question. Okay, good. So I covered that one. I think that's all the questions that I want to answer today. As for those about substitution and partial integration, we'll get to that tomorrow. Any more questions from the live audience? So I guess that's a good point to stop for today. It doesn't make much sense to start with those topics. We'll cover those tomorrow and see if you examine that. So I'll see you tomorrow. Have a nice day.